Yeah, so my name is Alan Gray. I work as a developer technology engineer in NVIDIA, which is it's a technical position where I work closely with external application developers to work directly on applications, porting, optimization, and scaling on GPUs. My particular background is in high performance computing, and over the years I've worked with a range of different HPC applications. More recently, in the last 2 years or so, my main focus has been on Gromacs. So that's what I'm going to be talking about today. I'll be talking about the work that we've been doing with Gromacs. We made some quite big optimizations that have become available in the latest version of Gromacs. So I'll explain why these optimizations were needed, what they are, how they work, and at the end of the presentation, I'll show exactly how to run Gromacs, enabling these optimizations to get the highest performance possible. And yeah, I should also add that I'm based in Scotland, in Edinburgh, in the UK. Okay, so please feel free, if anyone has any questions, you can feel free to jump in and ask them at any point, or we can spend some time at the end for questions as well. I think someone has their, that's better, yeah, okay.
Yeah. I suggest for the questions to write it on the chat, and you can stop whenever you feel comfortable.
Sure, okay, that's fine. Okay, so let me just get, okay, here we go. Yeah, so quick acknowledgement slide to get started, that this work is done as part of a collaboration with what we call the core Gromacs development team. Gromacs is an open source application, so anyone can contribute, but there is a core of developers who manage the software, and they are based in Stockholm, across several centres in Stockholm that are listed here. Okay. So I'll start off introducing the work. I'll give a high-level overview of the work that we've been doing and why it's necessary. I'll show some performance results to show the large benefits you get from this work. And then I'll go into a little bit more detail, followed by, as I say, a how-to guide as to how to run Gromacs with these optimizations at the end. So what is Gromacs? So Gromacs is, it's a kind of toolbox, if you like. It's a package that allows you to perform a range of different biomolecular simulations. It's actually, at the moment, it's it's proving to be very important with the current pandemic. Gromacs has been heavily used to try and understand if there's scope for developing new treatments, etc. Understand the different biomolecular mechanisms that happen within in relation to the virus, and there's a lot of research projects that are recently started using Gromacs as part of the efforts on COVID, and that's just one of the different areas as an example. As I say, it's used for a range of different molecular dynamics simulations, most of them biomolecular. So it's computational chemistry and biology. We have a strong focus within NVIDIA on Gromacs because it's such an important application globally. There's many scientists that use Gromacs all over the world, both within large-scale supercomputing centers, but also, just using their workstations. And Gromacs is, as we'll see, it's particularly well suited to GPU computing. So there's it's getting high usage both with many different types of GPUs across many different situations all around the world. It works. It's a fairly simplistic way of thinking about it, how it works at a very basic level, although the code is extremely complicated when you start looking into it. But essentially what happens is we have a bunch of particles, okay? a bunch of molecules or atoms, and these all interact with each other and move around to form the system that is being simulated. So the important thing is that the Gromacs will allow simulations to be performed such that these atoms move around and interact with each other in the correct physical way, so that scientists can understand accurately different processes that happen in nature. So the important thing is to calculate the forces between all the different particles, and then once you have the forces, then you can work out how each particle should move based on the forces that are being exerted on it. So this is essentially Newtonian mechanics. And if you think you had a very simple system with two positively charged ions, then these would repel each other. Of course, we have hundreds of thousands or millions of atoms in real simulations that all interact with each other. So calculating forces is the most expensive part of the simulation, and the reason is that we have many particles, and every pair of particles can potentially interact with one another. So that's many different interactions overall in the simulation. Now, the forces do get weaker with distance, so particles that are closer together have a stronger force with each other, and that gets weaker as the particles get further apart. But it's not possible just to ignore long distance forces. You can't do that while still having an accurate simulation. You have to take it into account. But as we see, there are ways that you can, sort of tricks that you can improve efficiency by taking advantage of this fact. So force calculations in Gromacs typically fall into three different classes. The first one is non-bonded forces, which are the way that you would think that the way most match to what I described in the previous slide, that each pair of particles interacts with every other pair directly. Just calculate the forces directly. And this is what is done for all particles that are within a certain distance from each other. Within a certain cutoff range, then we just calculate all the forces directly. As I said, at longer distances, the forces get weaker, and we're able to do some approximations to make this the simulation more efficient. We use something called PME, particle mesh Ewald, which involves doing Fourier transforms from real space into Fourier space, where we can do the calculations much more efficiently for accounting for long-range forces. And we also have there's actually quite a few different other types of forces, but the most important in terms of computational expense are what we call bonded forces. And these are required due to specific behavior of bonds between particles. For example, the harmonic potential if you have two covalently bonded atoms that are stretched, like a string-like potential. So Gromacs was actually one of the first applications to be GPU accelerated quite a few years ago, back in the early days of general purpose GPU computing. And the reason was that at that point, when you ran these calculations on a CPU, then the non-bonded forces were just extremely dominant. They took up almost all the time of the simulation. And they're also very well suited to porting to the GPU. So in the early days, the non-bonded forces were ported to the GPU, and that was all that was ported. So it was a limited section of the application, which had a big effect in terms of overall acceleration, and the overall application was able to get much better performance on GPUs. Now, what's happened since then is that the GPU has become faster, such that the other forces became more important. Just due to Amdahl's law, if you accelerate one part of an application, then the parts that have not been accelerated start to become more important. So in more recent years, the PME and the bonded forces were also ported to the GPU. So all the main forces, even in the previous version of Gromacs in 2019 series, all the main forces were ported to the GPU. Some of that involved some of our work. But as we'll see, now these four calculations, all of them are now so fast in modern GPUs that all the other parts of the simulation have now become the bottleneck, or before this work that I'll describe, all these other parts became the bottleneck. And especially if you want to use multiple GPUs for the same simulation, the performance was far from optimal because of the overheads involved with all the other parts of the the simulation, including the communications that are required, especially when you have multiple GPUs. So I'm going to describe the work that involved porting all the remaining significant computational sections to the GPU, and also perform inter-GPU communications directly on GPU memory space. So previously, the communications were all handled by the CPU, and there was staging from GPU memory to CPU memory, and NPI was used between different CPUs in order to do these communications. That was an overhead, a bottleneck. We've moved all to use GPU direct communication, so we can use peer-to-peer memory copies to copy directly between GPU memory spaces. And when we do that, especially if we have systems that have NVLink, very high bandwidth interconnect within our nodes, then we can get very high performance. Okay, so does anyone have any questions at that point before I go into more detail? I don't have my chat window open, so I can't see if there's any on the chat. So if there are, can both of you read them to me? Yeah.
Yes. So first, everyone see the slides? We had a few people that couldn't see so only the first slide. I hope that that was solved. If any of you have any additional problem, try to rejoin or reload the page. Hopefully that will be solved.
Okay. Okay, thanks. I'll move on then. Okay. Okay, so this slide here shows a screenshot from using the NVIDIA profiler. If anyone's not used the profiler before, I'd highly recommend it. It's really the best way that you can understand an application performance is to profile it and look at the output in the profiler. These screenshots are using the old version of the NVIDIA profiler, NVVP and NVProf. We now have the new Insight version of the profiler, but it's essentially equivalent in terms of what you would see here. So you can use either to get these pictures at the moment. I'm just using the old one because I did this a little while ago. So what I'm showing here is that this shows the profiler will show you a timeline of what's happening on the GPU. So the time runs from left to right. It's a bit like thinking about looking at a music score or something like that, time running from left to right. And all these things are events that are happening related to the GPU down here. The important part to look at here is the compute line, which shows all the compute kernels that are running on the GPU. These red parts are just things that I've superimposed here to show places where the GPU is not doing anything, where it's idle. And the more parts you have in the timeline where the GPU is idle, the less efficient overall your GPU code will be running. So this is actually showing the current version of Gromacs, but on an old architecture. It's on a KEPLER architecture, which is quite a few years old now. And you can see on this old architecture, you can see that the force calculations, which are these big, well, actually, all of these kernels here are different types of force calculations. This one's the non-bonded, let's say. These are the PME. There's a bunch of kernels here, including the Fourier transform, and this is the bonded one here. Yeah. So anyway, you can see that actually on an old architecture, things are actually quite efficient because the forces take so long. The forces have such, they're taking up a lot of the timeline here because there's a lot of computation to do in there. And there are some parts of the timeline, as are highlighted, that are empty, but overall the timeline is it shows the GPU being well utilized for most of the time. But if we contrast that with the same case, but on VOLTA, so this is on the new, well, we've just announced the even newer Ampere architecture, but until Ampere was announced, VOLTA was the most recent architecture. You can see this is exactly the same case, but you can see the difference here in terms of how fast the GPU is performing these force kernels. So what I've done is I've also augmented this with some dotted lines that show the different time steps. So Gromacs works by iterating many time steps, simulation time steps. And you can see the time taken here on Kepler has been squeezed right down. These are aligned, these timescales. So you can see the times is now being squeezed down to a much smaller area. So the simulation is running much, much faster on VOLTA. And the reason is that all these kernels are a huge amount faster going from Kepler to VOLTA. So that's great, obviously, but the problem that we've been addressing is that there's a lot more red on this timeline. As I've augmented this, where the gaps were, I've kind of highlighted where with these red lines here. So these gaps here show room for improvement, places where the GPU is not doing anything. And the reason that it has these gaps is because one of two reasons. One is that it's waiting on data being transferred over the PCI bus, which is these kind of browny yellow entries here, or it's waiting for the CPU to complete work, which is, for example, this gap here where nothing else is happening. And this is all just showing on a single GPU. Our work has been to improve this situation and allow the GPU to be busy, basically port more stuff to the GPU to allow it to remain busy all the time and to have everything accelerated so that the time step will be reduced even further in time and our simulation will be faster. So here's a cartoon of what's happening within a single Gromacs time step. As I say, the code is in reality much, much more complicated, but this gives you a high-level overview. So what happens is these three things here, the different types of forces, and these can all be overlapped with each other. So that's why they're shown in a stack here. And then when the forces are calculated, then what you can do is you can go ahead and you can update the positions of your particles. But in the previous version of Gromacs, it was only the force calculations which were accelerated. So green means GPU here, this means accelerated, and blue means things that are happening on the CPU, okay? There's two different blue areas here. One is called BO for buffer ops. This is just some internal transformations. I don't need to go into details of these. The other one is updating constraints, which is the part of the time step that updates the atom positions based on the forces that are exerted on them. And because these blue parts are on the CPU, we also need data transfers between GPU and CPU, which we've called H to D, host to device, or D to H, device to host, to get the data where it's needed for the different parts of the time step. The problem is that, and then when you reach the end of here, you repeat over and over again many times. The problem is, as I say, because there's different parts of the time step on different parts of the hardware, we need these expensive red parts. And also just because the CPU is relatively much slower than the GPU, we're having to wait longer for this part of the time step to complete, and that's what that gap was I showed you in the previous slide. So the solution is just to move everything to the GPU, and it looks much better because two reasons. One is the CPU part goes much faster because it's on the GPU now. We've moved it to the GPU. And also, we don't have any need for any PCI. There's no red here now because everything is on the GPU. We can just keep the data on the GPU for the whole time step, and then it's already there for the next time step. We don't have to ship it backwards and forwards again between the GPU and the CPU. So that's where the performance boost comes from for the single GPU version, at least. And we can see that in action here. So this top timeline is the same one that I showed earlier, and you can see we had all these PCI transfers, the yellowy brown color here. Some of them were actually getting overlapped anyway, which was fine, which meant that they weren't exposed and causing gaps. But some of them weren't. For example, this one and this one weren't overlapped, so that's why we had these gaps here in the compute part. And we also did this extra gap for the updating constraints part of the time step. That's all disappeared now with the new version. The GPU is much busy, it's getting utilized all the time. Much of it is actually getting overlap across the different types of force calculations. That's why we have multiple things happening at one time. And as a result of that, the time step, which was originally this size here, has now been shrunk down to this size here. So we have a performance boost. This is reflected in the overall performance of Gromacs for this case. So that's quite a nice boost, but as we'll see, when we move to multi-GPU, this is all single GPU, then things get there's much bigger of a boost, as we'll see. Multi-GPU is more complicated because we have to assign different parts of our calculation to different GPUs in our server. Now, Gromacs has two levels of decomposition for multi-GPU. The first one is a task decomposition, where it assigns the PME force. As I say, there's these different types. There's three types of forces: non-bonded, PME, and bonded. And Gromacs can assign the PME forces to its own GPU. Okay, so that's a task decomposition. And then the remaining GPUs can then be assigned the rest of the forces, and these are further decomposed such that parts of them are calculated across each of these remaining GPUs. Okay, so in this case, what I'm showing is a 4 GPU simulation where we have 3 PP GPUs, each of them doing a third of the non-bonded and bonded forces, and the PME GPU is doing the PME forces. Okay, now a limitation at the moment is that Gromacs doesn't have the functionality to decompose PME forces across multiple GPUs. So that means that we typically get to a scale where we can't get any higher at the moment with the current version of Gromacs. And that's something that we're looking at the moment in terms of improving that. But the problem is that the PME forces actually require Fourier transforms, which require all-to-all communications, so they're not particularly scalable. But yeah, that's something that we're looking to try and improve in the future. But at the moment, we're limited by having a single PME GPU and multiple PP GPUs. And it turns out that 4 GPUs is typically quite a good scale, quite a good balance to run Gromacs on because of this behavior. Sometimes we can go higher, but typically it won't scale a huge amount higher than that. For these, there are some types of Gromacs calculations that only have PP and not PME. These are called reaction field calculations, but these are less commonly used in science. They can only be used for certain things. And these can scale better. Okay. So this is the equivalent of the previous slide where I showed what we've done to improve things. We've gone from having, right, so at the original code, again, we just had the forces on the GPU. We had all this stuff on the CPU, which we've moved to the GPU in the same way as the single GPU. But in addition, for multi-GPU, we have to communicate data across our different GPUs. There's 2 types of communications. There's communications that occur between the PP and the PME tasks. So we have data that goes from the PP to the PME task to allow the PME forces to be calculated. So this is all the atom positions that we have to transfer at the start of the time step. We then calculate PME forces and transfer those forces back to the PP GPUs at the end of the time step. In the meanwhile, the PP GPUs are calculating the other types of forces, which end up being combined with the PME forces here in these buffer ops. And the MPI, because that's decomposed across multiple GPUs, we have MPI communications that do halo exchange type operations between the multiple PP GPUs, where the edges of the data are exchanged, so that if a particle is at the edge of its domain, it will then interact with particles that exist in another domain. So we have to have that edge data transferred between GPUs on every time step. So in the original code, this was all done on the CPU. Again, it's all blue. All the data was transferred across PCI, everything, only the forces on the GPU, but there was PCI transfers and CPU MPI communications as well as the CPU compute. That's all been ported to the GPU. So in addition to the new GPU kernels for doing the computation here, we also have GPU communications, so we can do communications directly between GPU memory spaces. We have different mechanisms for doing that. The mechanism that I'm talking about here is using direct CUDA memory copies. So if we're all on the same node here, we can use CUDA memcopy to transfer data directly between GPU memory spaces, even if they're on remote GPUs. And it will automatically use fast NVLink interconnect if that's available in the server. So these are much more efficient communications than we had previously. So I'll show you some performance results before going into a little bit more detail on the implementation. After these performance results, I'll take a gap to answer any questions as well. So these performance results are all on a multi-GPU, 4 GPU, using a 4 GPU server where we have NVLink connections between all the GPUs, which are very high bandwidth relative to PCI. And then we can connect into 2 CPU sockets using PCI on the server. These are all NVIDIA V100 GPUs. So this is the multi-GPU timeline here, and I realise this is getting a bit more complicated now, but you can see the picture again, looking again where I've superimposed these lines showing the different time steps. When we're going from the previous version of Gromacs without our optimizations, the time step takes this long. When we switch on the optimizations with the new version, then the time step is it's several times, so 3.5 times faster here for this case. And the reason is, on multi-GPU, there's a big overhead from doing the update and constraints part on the CPU, because this server because we've now decomposed across multiple GPUs, but we have got 4 GPUs in the server and only 2 CPUs. Any CPU parts are becoming a bottleneck due to the imbalance there. Oops. Sorry. So we've got rid of all that. This big gap, which was CPU work, has now been replaced with a few new kernels down here, which you can see that they're a huge amount faster than when you're operating on the GPU. We've also got rid of the memory copies here, the PCI transfers here, and replaced those with very fast NVLink transfers, which are on the PME GPU. We're showing the PME GPU down here. So what I've shown in each of these cases is just one of the 3 PP GPUs plus the PME GPU. So I say there's 4 GPUs, where the other 2 that are not shown have a profile the same as this PP GPU. Okay. So let's see how that translates into overall performance improvements. I'm going to show 3 different scientific cases which range in size from about 100,000 atoms up to about 1 million atoms, and we chose these that kind of span the typical sizes that are used by scientists at the moment today. So first of all, showing the 4 GPU results across the 3 cases. So the version on the left, 2019.5, is been normalized to 1 to show you what the old version did before these optimizations. And we're showing here speed up, which is so high is good, and we're showing how much improvement we've got with these optimizations across these different cases. It's ranging from just over 2x for the smallest case up to just under 3x for the largest case. From where we were from the previous version, due to these optimizations. So that means, so for STMV, we're able to run 3 times faster with the new version for this case. As I said earlier, the single GPU, we also have a boost. It's not so dramatic as the multi-GPU, but it's still significant, around 1.4 to 1.5 times faster than we had previously. Again, and typically what we see is that the smaller, we're getting a bigger benefit for the larger cases, and that's something that we're trying to improve going forward, is to get the smaller cases, improve the benefit for those as well to a higher degree. How does this compare to CPU? So this is comparing here, the baseline here is 2 Intel CPUs, Intel Gold CPUs, so two CPU sockets has been normalized to 1 for the 3 cases, and you can see if we use 1 GPU, we're getting around about 5 times faster for these cases, slightly less, so just under 4 times faster for STMV, and if we use 4 GPUs, we're getting up to for the largest STMV case 12 times faster than using 2 CPU sockets, and again we're hoping to improve the smaller cases going forward to get them looking more like STMV. Okay, good point to take any questions if anyone has any at the moment. Again, because I'm sharing my screen, I can't see the chat, so if there are any, if you wouldn't mind reading them out.
Any questions? I suggest to write on the chat. Meanwhile, I don't see I don't see any questions, so
that's fine. I can just continue and we can get them.
I can continue. Yeah.
Okay. Right. So I can see a question just popped up on my screen actually. Right. So the question was, with this optimization, you're constrained to within a single node. Yes, the answer is With the release version of Gromacs, the first thing we did was we implemented these using, as I say, direct CUDA memory copies, which are restrained, so we're constrained to within a single compute node. But I have a slide in this at the end of the presentation. We've recently now enabled this for multi-node as well with a patch. So you can get a patch to Gromacs that enables it with multi-node, and it will use CUDA-aware MPI to allow the multi-GPU communications so that this can be used across multiple nodes as well. Now the issue is, as I said, that typically Gromacs doesn't scale particularly well to multiple nodes because of the bottleneck on the single PME GPU and the communications that are required to go between that. So whilst it operates, or you can get it to operate on multiple nodes, the scaling is typically not particularly good going to multiple nodes. It typically works well on a single node fat node scale. And actually, most scientists that are using Gromacs they're doing what we call ensemble operations, where they're doing many different simulations, and so they typically use a single node to do each simulation, and then they'll run many simulations across the multiple nodes in that way. So yeah, so that's where we are with that. Okay, so a little bit more details on the development. Right, so I'll go through this part quite quickly so I can spend a bit more time before we finish on the how-to part of the presentation. But yeah, we did this work in collaboration with the core Gromac developers. One of the first things we did was we allowed the bonded force to be offloaded to the GPU, so we created a bunch of new kernels, which have now been merged into one kernel for better performance. We did the buffer operations, which I say are internal transformations and reductions within Gromacs. So these all had to be ported to GPU, so that involved quite a lot of refactoring, new kernel development, etc. We ported the update and constraints part of the time step to the GPU. That's several new kernels and again some restructuring and refactoring. And we created these new mechanisms to do multi-GPU communications. As I say, at the moment these are using CUDA peer-to-peer memory copies. I'll give you a little bit more detail on this in a second. But we now have a patch to instead use CUDA-aware MPI to allow this to go between nodes as well. So say there's two different types of communications. There's those between PME and PP tasks, and there's also halo exchange communications between P tasks. And it's a similar story that we enable these using peer-to-peer memory copies as well. They're a little bit more complicated, the halo exchange, because they involve non-contiguous memory. So you have to do buffer packing and unpacking before the memory copies can happen. So that's all enabled on the GPU as well. So the PP to PME communication, so what we had originally was, this was all staged via the CPU, so the data had to be transferred from the GPU to the CPU, then everything was done on the CPU, including the MPI, and eventually it was transferred back to the remote GPU to then be operated on. New development allows us just to do direct transfers between GPUs. So it's two levels of benefit. One is it makes everything much less synchronous. It cuts out the CPU involvement so that this can all happen on the background on the GPU. And also, when we have higher bandwidth links available, then we can take advantage of those to get faster communications. The halo exchange is similar in nature, but as I say, it's a little bit more complex because we have to do buffer packing and unpacking on the GPU. And in order to do that buffer packing, there was originally code that worked out which indices were involved, or at least there was code to do the buffer packing on the CPU. So we leveraged that code to, rather than do buffer packing on the CPU, we create an index map, so an array of indices that are involved in the transfer, which can then be transferred to the GPU such that the buffer packing can then operate on GPU memory using that array of indices. Now, we just use CPU code to generate that index mapping. And that's fine because we only have to do this once every 100 time steps or something like that. So it's infrequent and it's a small amount of data, so we don't have to do this every time step. So it's not a big overhead. Once we have that in the buffers, we can then just transfer these directly. I won't spend much time on these, but this just shows you the tasks that are involved, and that's this original CPU path, relatively straightforward, but things get more complicated when we do this on with the GPU code. We have, let's see, Gromacs has multiple streams, but it does different parts of the calculation. But it tries to be as asynchronous as possible, so there's a lot of events. CUDA events, CUDA streams that have to be synced together, and this is now across multiple GPUs. So we have GPUs that are passing events between each other and syncing remotely on these events. Things are even more complicated for the force part because there's a reduction involved in there as well. Okay, let's move on to the how-to guide. So the optimizations are not enabled by default. They're very new, so they're not on by default yet, but you can switch them on with some environment variables. The idea is that we'll get feedback from users such that we can switch them on by default in the future version. But we advise users that because these are new, then they should carefully test them for their own simulations against results from the default path, just to make sure that everything's okay. So here are the environment variables needed to switch them on. Right, so first of all, Gromacs should be built using, so there's two ways to build Gromacs. You can build it with, there's a switch, a CMake switch, an MPI switch that you can switch to on or off. If you switch it to off, then Gromacs requires MPI. So if you switch to MPI, CMake switch to off, it uses its own internal MPI implementation, which is called thread MPI. So it's an internal MPI implementation which is built on pthreads that can operate within a single node. So for the release version of Gromacs that you can download, then you require that version to run these optimizations. As I said, you can get a patch version that allows using an external MPI library. I'll come to that soon. But for the release version, you have to use thread MPI, and it has to be within a node. And then you switch on these three environment variables to get these optimizations. The first one enables the Halo Exchange multi-GPU communications direct on GPU memory space for the PP task. The second one switches on the GPU direct communications between PME and PP task. And the final one switches on GPU porting of the update part of the time step. So switch them all on to get all the optimizations. If you're on only a single GPU, then the communications part is not relevant. So the only important thing is the update part has to be in the GPU. So you can either use this environment variable or you can use the -update GPU flag instead. There was one point, the reason that I don't have the -update GPU flag here instead of this environment variable is I think previously you needed this, but I think now we're in a situation with the latest release that you could alternatively use the -update GPU flag for the multi-GPU case as well. But yeah, there's no harm in you switching on that environment variable anyway. It's also important to make sure that all the other forces are on the GPU. So just have -non-bonded GPU, -bonded GPU, and -PME GPU switched on. Some of these are on by default anyway, especially the non-bonded on it. But yeah, I think the non-bonded is always on by default, but the other two depend on whether you're on single or multi. I think the bonded is not on by default, and the PME depends on your single multi GPU. So play it on the safe side. Have all these on your runtime just to make sure everything's on the GPU. If you're a multi-GPU, you also need to have this -npme1 to make sure that only a single GPU is assigned to PME. Otherwise, you'll just get a runtime error saying that multi-GPU PME is not supported, as I discussed earlier. This is only important for scientists that are creating new cases to run on the GPU. When you're creating an input file, you use the Gromacs preprocessor grompp to create the input file, which is a .tpr file. So when using the preprocessor, you create an MDP file that is a .mdp file that is used as an input to the preprocessor, which goes on to then create the TPR file that's used by Gromacs MD run. It's important to set the constraints to H bonds rather than all bonds. This is the preferred way to constrain the atoms going forward. It's a relatively new option in Gromacs, but it's required for all our optimizations to be triggered. Otherwise, you have extra communications with all bonds and things are suboptimal. So this should be set to H bonds in order to get our optimizations working. So the command I used to get the results that I showed earlier, this is Gromacs is one of the things that needs to be improved going forward is to make this more user friendly. It's quite complicated, but I'll show you what each of these different parts are. I've already showed you this line here, which is just saying that all the forces should be on the GPU, and we should have one PME task here. The other parts I'll come to in the following slides, just to show you what they mean. I'll just So I'll just go through sort of building up these options here. Let's go back here actually to get started. So -v just says give some verbose output to show you what's happening as the simulation proceeds. How many time steps we're using. This is a benchmarking run, so we don't want to run for too long, but we want to run for long enough for any load balancing, etc. to take effect. Excuse me. We want to reset our timers at some. We don't want to include the timers for all the time steps because I said the first lot of iterations it will be doing some load balancing, etc. that you don't want to include in your time. What you want to include is just the last, say, 1,000, or in this case, the last 10,000 time steps, because that's what's representative of what a full work run would be if you just kept running this simulation for a long time. No conf out means you don't want to have the simulation write an output file as part of this benchmarking, because again, for a real simulation, the output would come right at the end after a long run, so it wouldn't be significant. In this case, I want to run with 4 MPI tasks, or in this case, 4 thread MPI tasks, with 10 OpenMP threads per task, and that's just because I have 40 cores, CPU cores on my server, and I want to use all of them, so that's 4 times 10. I'll come back to the NST list. So if I run this, to give an example, if I get the wrong settings here, I'm running on, again, I've got these settings right, I'm running 4 GPUs with 10 OpenMP threads. I'm not doing any auto-tuning here. I'll come back to that. But I'm not specifying any of where the forces should be, etc. And I get performance here of around 7 nanoseconds per day. Okay, just switching the forces, making sure all the forces are on the GPU. Okay, so the non-bonded is by default, but putting the other 2 on. Yep. Someone got a question? No? Okay. Putting the other forces on the GPU, it goes from 7 nanoseconds to 43 nanoseconds. So you can see that the big difference you get, or the big hit you'll get if you don't get these options right. Okay, so you have to be careful to make sure everything is on the GPU, or the forces. Okay, so we're at 43 nanoseconds per day there. Now we're activating the new optimizations here by switching on these environment variables, and we're going up to 88 nanoseconds per day. So we're getting a factor of 2 improvement here for this case, just by switching on these new optimizations, which do the stuff that I mentioned earlier in this talk. So again, we've gone from 7 nanoseconds per day for doing a very naive command line up to 87 nanoseconds per day for getting these optimizations on. But we're not finished yet. Things are still not quite optimal. I'm going to allow it to do some auto-tuning to get a good balance between PP and PME tasks. So that's why I've removed the no-tune PME flag, and I'm allowing a larger number of time steps in order for it to get that auto-tuning done. This is very dependent on the case, okay? Depends how well balanced the case is to start with. So this had effect for some cases and not for other cases, but the case I'm showing here, which is the cellulose mid-size case, is getting a huge boost from doing that up to 147 nanoseconds per day from doing this auto-tuning. There's one thing I didn't. Oh, there's 2 things that are contributing to this big boost here. both the auto-tuning and also I've set this NST list 400. So the NST list is a parameter that allows you to decide how often you recreate the neighbour list, so decide which particles are within a cut-off range for the non-wanted forces. You have flexibility to do this because it doesn't change the accuracy of the simulation. So by default, often a case can have a very low value of NST list, which means it's recreating this neighbour list every small number of time steps, for example, even as low as 25 time steps, sometimes 80, sometimes 100. But every time it recreates the search list, it's doing a bunch of other stuff in that irregular step as well, and it's doing memory allocations, etc., that can be expensive. So what I'm saying here is I want it to do that less often, and I can get away with that because it doesn't change the accuracy of the simulation. But this just really has to be tuned by hand. I just went with this number 400 because I tried a bunch of different options, and this turned out to be the fastest for this case. The best thing is just to experiment and work out where the sweet spot is for the NST list for the simulation that you're running. And it can have quite a big effect. Okay, the multiple compute nodes, my last slide. So, yeah, as I mentioned, we've recently enabled this on multiple compute nodes. You have to use a patched version. So there's a branch on GitLab that I've linked to here. When you have that patch, you can then compile with -D with this CMake flag. It's with MPI switched to on, which means you want to use an external MPI library rather than the internal MPI library. You need to also add another CMake option to switch CUDA where MPI on to enable the new code path. And once that's on, you can then just run in the equivalent way, but the difference being rather than doing GMX MD run, you'll use a standard MPI launcher like MPI run -N4, and you get rid of this -NT MPI4 here because you're basically moving from the thread MPI into external MPI, so you're doing it as a proper MPI job. Okay, then the rest of the options will be the same. As I mentioned, multi-node scaling will be limited due to the bottleneck on the single PME task. Okay, so yeah, summarize, we've been doing a lot of work to improve Gromacs, and this is available in the latest version. And we get big performance improvements with that. We're still working on Gromacs, trying to stabilize and further refactor these cases, just improve the code quality, make sure everything's working properly before these become default. As I say, we're looking at PME decomposition to try and allow us to scale better across multiple nodes. Yeah, so we've already done this part. We've removed the single node limitation that's available in a patch. And we're looking at further improvements as well. Okay, so that's me done. Any more questions?
Thank you, Alan. If any of you have any questions, you can either speak or just type it in the chat. We'll wait a minute. Still have a few minutes more.
The environment variables. So the question is, the environment variables set, are they necessary at compile time or runtime? The environment variables are only necessary at runtime. So at compile time, you just build in the normal way. So if you're using the release version, then you should use the thread MPI. If you're using the patch version that allows external MPI, then you just need to put that extra CMake flag in to switch on CUDA where MPI. By the way, it's worthwhile. So if you're doing this for the cluster competition, even if you're running in a single node, it's worthwhile switching on. It's worthwhile trying with external MPI anyway, because sometimes it can be faster. Because there can be the difference in the way that it runs is that when you run thread MPI, it's running it all within a single process. So it's, let's say, Gromacs has its own MPI implementation that uses a single process but multiple threads, multiple P threads. If you use external MPI, you use multiple processes, and that can end up with some less overheads within CUDA APIs, because CUDA APIs can be a little bit extra overhead if they're running on multiple threads in the same process. But it might not have much effect. Depends on the case that you're running, whether you really see that effect or not. Okay, I have another question. Let me just. I have a slight problem. My mouse has disappeared and I can't scroll up to see the start of the question. Oh, I got it now. Yeah. Okay. So, say that most of the time you're running the kernel on GPUs, are you thinking about using P2P communication outside the node to the new JX100 to scale outside the node? Another possibility would be to taskify communication phase and computation phase and store operations and highlighting by overlapping. Right. So we already. So I'll answer the second part first. Okay. That we already do overlap communication and computation. I didn't go into the details there, but the way that Gromacs works is that for the Halo Exchange communications, then it operates two streams, what's called a local stream and a non-local stream, where it does the non-local parts in the non-local stream that are overlapped with the local stream. So that means the communications get hidden behind computation. The PME and PP communications, the PME to and from PP communications, they also get overlapped behind the PP part, but there's a data dependency there that they can't be overlapped behind the PME part because it's the whole lot of data. It's not just, the Halo Exchange is only part of the domain that gets transferred, but for the PP PME you need to transfer the whole domain. Scaling outside the node, so we can, with CUDA aware MPI version, CUDA aware MPI is really nice because it actually will just automatically take advantage of whatever network mechanism exists in our hardware. So if we run across multiple nodes, it will use InfiniBand, and it will go directly into the InfiniBand adapter using our RDMA to get as high bandwidth and lowest latency as possible. In principle, if you had a system that had external NVLink, for example, then that could be automatically used by OpenMPI as well. But a disclaimer on that is that as I say, what you do end up getting limited by this PME task because you have a single PME task, and at some point that just becomes the bottleneck, and we can't go any faster than that, even if we do have faster communication. Okay. Okay, next question is, do you have access to nodes? Do you have access to nodes where the CPU and GPU are also communicating with NVLink? Right, so the only nodes that have access, that are really available at the moment where you have NVLink between CPU and GPU are the IBM nodes. And I personally, these are available on, for example, the big supercomputer like Summit in the US. I personally don't have access to that. I think we maybe have some internal machines that have it. But we've kind of minimized the CPU to GPU communication anyway, so that's not so much of a factor. It might make things a little bit faster, but it's not. We've minimized that with these optimizations, so it's not a big factor. Okay, can you please re-explain what the NEST-list option does? I missed that. Okay, yeah, sure. So when we run Gromacs to say it does the non-bonded calculations between all pairs of particles that are within a certain cutoff range of each other. Okay, and in order to do that, it has to know so each particle has to know what other particles are within its cutoff, so it knows which ones to interact with directly. So it has what we call a neighbor list of particles, the list of all its neighbors, and that has to be recalculated every so often because the particles move around, so that a particle that used to be a neighbor might move outside the neighborhood, and other ones might come in. So it's basically the NST list says how frequently should you calculate the neighbor list. So if you say NSD less than 100, it means every 100 time steps, it will do a different kind of time step we call a search step that calculates the search list. And it's not, that step has a lot of other stuff in it as well. Like, we're just kind of leveraged because it also, for example, redoes the domain decomposition, and associated with that, it means that a lot of different functionality is reinitialized on those search steps. So there's quite a big overhead with those search steps in terms of compute. So you want, in that sense, you want to have them as irregular as possible. But then on the other hand, if you have them too irregular, then the neighbor lists become outdated, and you end up doing a lot of calculations with neighbors that you don't need to anymore because they've moved out with the neighborhood. It doesn't affect the accuracy of the simulation. It just means that you could be doing things more efficiently. So that's why it's good just to tune that by hand to get the best value. The question: does this change anything? I don't know. I don't have the. I think. Okay, that's in association with the NVLink. I think I've answered that already. Okay. When a GPU is not connected via NVLinks, are we still able to? Yes. Are you still able to enable the GPU force? So the GPU force update default GPU has nothing to do with NVLink. That is only saying that we want to put the force, the update part of the calculation onto the GPU. So that is a compute part of the time step. The bit that did the update and constraints part of the calculation originally in the CPU, by setting that environment variable, we say we want the GPU to do that. And that's kind of, it's not related to NVLink. It doesn't involve any communication. The point is, though, that you want to have that set. It works well in conjunction with the other optimizations, because if we have that in conjunction with the GPU communication flags, then it means that we can keep the data resonant on the GPU memory space for the whole, across all the time steps. If we have any of these flags unset, then we end up having to do PCI transfers, either such that the communications can happen, or to do the update on the GPU, or the CPU, sorry. So we want to get full performance, we want to set all of these flags so that the update part of the time step, and hence the whole time step, runs on the GPU in terms of compute kernels, and also the communications go directly between the GPU memory spaces. They don't have to be staged back via the CPU. By the way, if you have a system that doesn't have NVLink, these optimizations are still beneficial. Not quite as beneficial, but still beneficial, even if you just have a PCI-based server, because of the extra asynchronicity that they offer. Okay, what does the -DD option to MD-run mean? How does it affect the run? I actually can't remember. I've not used that option. It's not something that I've had to. Oh no, I do know. Yeah. So right. So you can specify. So as I say, I've not used this because we can specify things either in the source code or in the input files as to how we want things to be decomposed, etc. But Gromacs uses some heuristics with regards to how it does the domain decomposition, and it's possible to overwrite those with the -DD flag. So it's not something that I've used personally much for these cases, and it's probably quite specific on a certain case whether it has any effect. Gromacs does have its own load balancing functionality, so it does try to balance things automatically anyway. But if you have a case that's particularly unbalanced, like for example in your system, you have one parts of the system have very high concentration of molecules relative to other parts, then it may be the case that you can do better manually by specifying the -DD option. But the cases that I've worked with so far have been quite balanced, so it's not really been an issue for me. Next question. So the GPU direct communication is enabled with DD comms. This is the one related to NVLink. Yeah, so there's two options. Both of the options that are _comms at the end are related to NVLink. That one there is to do with the Halo exchange communications that happen between PP tasks. The other one, the PME comms, is related to the data exchange that happens between PP and PME tasks. And we have these two, because I say we have these two levels of decomposition in Gromacs. We would require data to be transferred both. The two levels of decomposition are that We have a task level decomposition between PP and PME tasks. And we also have within the PP tasks, which PP means particle-particle, these are the tasks that do the bonded and the non-bonded forces. These can be further decomposed across multiple GPUs, and for that you need a halo exchange communication. Okay. Well, I think that's all the questions that are there then. Oh, sorry. There is one more question. What parameters options could we possibly experiment with in addition to what you specified to affect the performance? Well, what I would suggest is you start looking at the profiles and work out what the code is doing and try and work out, for whatever case you're using, if you can see any more optimizations. Don't, start looking in, potentially you could start looking at doing source code optimizations. With regards to just looking at runtime, I've given you the ones that I think have the biggest effect. I don't have any that come to mind that are obvious to give on top of that. But again, it depends on the case, and it possibly depends on the hardware as well. So I'll use the slides from this presentation to get an idea of what I did to understand the performance looking at the profiler, and to understand when I thought I had good performance. And then you can then hopefully work out if that's also true for your case, or if you think there's any further room for improvement. Will a recording of the webinar or slides be available?
Yeah, I will upload the link to the recording, and you can view it online or download that. Also the slides. Okay, so at this point, Alan, I would like to thank you for being with us. It was very good presentation and some very good hints for the teams. And for the teams, if you still have questions, you can contact us on the Slack, and we can try to help whenever we can. Okay. Okay. So thank you, everyone, and we'll see you next week on Tuesday, if I recall. Yes, Tuesday with Elmer Ice, same time. Okay. Okay.
Thank you. Bye bye.
Bye bye.